right, our final speaker in the young person section of the program is Dan Hudson, local content here from Toronto. We'll speak on deformation spaces of Lie groupoids.
Okay, so thanks to the organizers for having me and organizing the conference locally. What a treat. So I've talked about this a couple of times, and I like to think that every time I improve upon it a little bit, but what's also happening is the amount of time I've been given to speak also shrinks. So maybe the perfect talk will happen when I'm not given any time at all. So, so today, so I'm going to talk to you about deformations of Lie groupoids, and strictly speaking, how do I deform a groupoid to get a groupoid? I mean, as was sort of discussed in the previous thing, sort of implicitly, we want to do some sort of deformation procedure to understand operators, and one of the key features, which wasn't mentioned, is that we start with a pair groupoid and we wind up with a groupoid, and so I wanted to understand when does this work in general. So to start the story, one looks at something called the deformation to the normal cone. So how this works is you start with a smooth manifold M with some smooth embedded submanifold N, and we denote by I sub n its vanishing ideal. And so what Nigel and his past student Ahmed Reza Haj Saidi Sadiq tell us is that, okay, we should look at this associated graded algebra, which is given by the direct sum of functions which vanish to order k modulo functions which vanish to order k plus 1. We should look at the Riesz algebra, which is finite Laurent polynomials in Z, such that the function, which is the coefficient of Z to the minus k, vanishes to order k along n. And then what we should do with this is, well, we should look at the character spectrum. So I don't know if Nigel and Ahmed Reza told us this fact, but they certainly told me this fact, is that if I look at the character spectrum of the associated graded algebra, I wind up with the normal bundle of n. And what they really told us, I think, is if I look at the character spectrum of the Riesz algebra, what I wind up with is a smooth manifold called the deformation to the normal cone. And it comes with a surjective submersion onto R such that the fibers away from 0 are just M again, but the fiber at t equals 0 is the normal bundle. And so as a special example of this, if you apply this deformation to the normal cone procedure to M living inside M times M as the diagonal, you get the tangent groupoid. So to me, this was kind of surprising because it was kind of shocking that this thing could be a manifold. But the reason why it works is because we started with an embedded submanifold. So in particular, we have local submanifold coordinates. And if n is cut out by the coordinates x1 to xn, then the functions, the ideal of functions which vanish to order k, is generated by monomials of this form. And so what this prompted, I don't know if this is Richard Melrose's starting point, but this is my understanding of what Eckhard Meinrenken and Yanni Lazaida's point is well, they say, let's just take this as an axiom, and to do this, they packaged this as a definition, and they said, okay, well, let's just fix weights, W1 up to Wn integral, and let's define a weighting to be a filtration of the sheaf of smooth functions such that the functions of order I, this ideal, is locally generated by monomials of this type. So we can always find coordinates with this property. This sort of generalizes submanifold coordinates. And we're sort of saying that the function xi vanishes to weighted order wi along n. So this is some sort of structure that you can assign. It comes with some nice morphisms, namely the function, the smooth maps whose pullback on functions is filtration preserving. And what they also tell us is that the first term in this ideal, or sorry, the first term in this filtration is always the vanishing ideal for some smooth closed submanifold. And in this case, we refer to Mn as like a weighted pair, and we say that M is weighted along n if you want. Okay, so some examples. Well, of course, I mentioned you have this trivial example, which is just order of vanishing. But you can also have non-trivial examples. So for instance, you can define a weighting of R squared along the origin by declaring that X vanishes to order 1 and that Y vanishes to order 3. And the filtration that one gets from this looks like this. It's kind of a simple example, but as I'll show you, there's some meat to it. Okay, so as I mentioned, the key point or the key ingredient needed to define this sort of like character spectrum, Reese algebra business and the deformation of the normal cone is that we had these coordinates. So it all just works exactly the same. So given this weighting, which is given by a filtration, I can define the associated graded. I can define the associated Reese module, or Reese algebra, sorry. And what Yanni and Eckhard tell us is that if I look at the character spectrum, I get this thing, which they refer to as the weighted normal bundle. It's not a vector bundle, but it's still very closely related to a vector bundle. And I also get a weighted deformation space. So again, I get some sort of manifold with a projection from it onto R, such that the fibers away from t equals 0 just give me my manifold back, and the fiber at t equals 0 gives me this weighted normal bundle. Okay, so some examples. Well, I think the first, well, I mean, this is not the first example, but an interesting example is if one starts with a manifold whose tangent bundle is filtered by subbundles satisfying some Lie bracket relation, then this defines a weighting of the product m times m along the diagonal. And if one looks at the weighted normal bundle, you get this thing, and this is the bundle of nilpotent Lie groups exponentiating the associated nilpotent Lie algebra taken by direct sums of the quotients of the HIs. And the weighted deformation space factors like this. So this is the osculating tangent groupoid that was studied by Choi and Ponge, Van Erp and Youngkin, and also Olman Mosen. And a sort of similar example is if I start with a Lie group and I look at its Lie algebra and I filter the Lie algebra by subspaces satisfying a bracket relation, then I can do the same thing and I wind up with a very similar story. So in particular, in both of these examples, I started with a groupoid. Here it was the pair groupoid, here it was a Lie group. And what I wound up with was another groupoid. And so my question is, okay, if I just start with a Lie groupoid, I weight it along some submanifold, when is it the case that this thing and that thing are both groupoids? And we don't want them to just be some random groupoids. I want the groupoid to be sort of naturally defined in terms of functoriality. Okay. So probably everyone here knows this, but to sort of build some suspense and motivate my next slide, I have to do this. Well, what is a Lie groupoid? It's some manifold with some data. Namely, you have a submanifold, which we call the objects. We have a pair of submersions, the source and the target map. We have a smooth partially defined multiplication, and we also have a smooth inversion map. So, oh no, I mean, we're mathematicians, so we make names for things, so it makes sense that a weighting for a Lie groupoid should just come from putting the term weighted in front of everything. And that's what we do. But the issue is that as far as the theory of weightings was developed by Eckhard and Yanni, this word didn't make sense. This word didn't make sense. And okay, this word makes sense, but not really, because the space of composable arrows is not a product. It's a fiber product. So it's not clear that it makes sense to ask for this map to be weighted right off the bat. And secondly, well, sure, I can say this, and I can give a clear definition, namely that when I apply this weighted deformation functor to it, the output should be submersions, but okay, how do I check that? I don't know. So what did we do? We gave a definition. So we said a submanifold of a weighted pair is going to be a weighted submanifold if I can always find local coordinates which are simultaneously weighted and submanifold coordinates. And I say, okay, well, what do I want weighted submersion to be? Well, what is a submersion? It's a map that admits local sections. So let's just ask for it to admit local sections which are also weighted. And there's some reasons for why this is a good definition. First of all, because it's the obvious one. Second of all, if I had a weighted submanifold of a weighted pair, then it itself is a weighted manifold. And secondly, if I had a weighted submersion and R prime is a weighted submanifold of the codomain, then its inverse image is going to be a weighted submanifold of the domain. I'm also skipping some stuff for the lack of time, but we can characterize all of this stuff in terms of infinitesimal data too. It's not, this was the first definition we gave, but okay, there are several different characterizations of submanifolds and submersions in terms of the tangent bundle and whatnot, and we can express what this means in that sense. But let's look at some examples to also sort of express that there's something interesting going on. So if M is just weighted along N by order of vanishing, then the weighted submanifolds are exactly the ones that intersect N cleanly. So that's already something interesting. Another, pardon? So what I mean by intersect cleanly, I mean the intersection is actually a manifold, and the tangent bundle of the intersection is the intersection of the tangent bundles. It's weaker than transverse. It's weaker than transverse. Because, for instance, you could have a submanifold. Yeah, exactly. So another sort of interesting thing is a non-example. So in the previous example where I gave r squared the weighting by declaring x has weight 1 and y has weight 3, I can look at the parabola y equals x squared, and this is not a weighted submanifold, even though they intersect cleanly. It's not a weighted submanifold. And another example is if I give r the weighting as before, x has weight 1, y has weight 3, I could also give r the order of vanishing weighting along the parabola y equals x squared. And then the identity mapping from this r to that r is not a weighted submersion. So there's something happening. And finally, just for the purposes of a problem that I mentioned, if I started with a weighted pair, I can take its product, and the diagonal inside the product is always a weighted submanifold. Okay, so now we can go back to the slide before, where I wrote all these things down and said this is the definition, but the problem is I have a definition that I haven't defined. Now I have a definition for which I have defined all the words. And the only small thing I have to mention is, how is this weighted? Well, this is the inverse image of the diagonal in the pair groupoid under the groupoid anchor, which I'm assuming is a weighted submersion by this part. So this thing naturally is a weighted submanifold, and so it makes sense to ask for this. I should also mention that here, all I've asked for is that H just be some submanifold of G. Well, I've sort of used some suggestive letters, but it turns out that if the weighting is multiplicative, then automatically this thing is a subgroupoid. It's a Lie subgroupoid. So you can't just have multiplicative weightings along any old submanifold you want, which kind of makes sense. And so then, yeah, once you assume that this is the case, you get the groupoids you want. And actually, I should also mention, so part of the groupoid structure here is it's all determined completely by functoriality. So namely, the source and target here, in particular, are given by applying the weighted deformation functors to give me the source and target here. And actually, those two maps being submersions, which is necessary for a Lie groupoid, is equivalent to our definition of being a weighted submersion. So you can't do anything else. And finally, there's a whole infinitesimal story here, which I'm not talking about. But I just want to sort of, it's like the elevator scene in The Shining. There is more to be said. And namely that multiplicative weightings can also be differentiated. So we've figured out what the right notion of weightings for Lie algebroid is. This can be expressed either in terms of the sections, either in terms of the Poisson structure on the dual, or the sort of Lie algebroid de Rham complex. And we figured out that you can always differentiate it. And we've also investigated the integration problem too. So in the examples of multiplicative weightings that I gave, I started with a Lie filtration, and this gave me a weighting along the object space. And so for instance, we've sort of learned that this is the best one can do. So a multiplicative weighting of a groupoid along its objects will sort of always be given by some filtration of its Lie algebroid satisfying some bracket relations. So the generalization of this, the generalization that this offers is if you want to deform along subgroupoids whose objects are not all of M. So subgroupoids whose objects are proper submanifolds of the objects of G. And so, yeah, that's all I have to say on this. So, well, that's not all I have to say, it's all I have time to say. So.